Okay, so we've been talking clustering, and now we're going to use kind of another clustering method, okay? And so we've already looked at, say, k-means clustering. And k-means clustering uses distance, Euclidean distance, as a measure of similarity. Okay. And we saw, some issues with that, and so kernelized k-means was a way to kind of get around some of the issues produced by using Euclidean distance as a measure of similarity. Today we'll introduce the EM algorithm, specifically in the context of Gaussian mixtures. The EM algorithm, the original algorithm, is a little bit more complicated. I think when we apply it for Gaussian mixtures, it's easier to grasp, and so that's what we'll focus on. But the EM algorithm allows not just the distance, but kind of includes the shape of a Gaussian distribution to help us determine whether a point belongs to a certain cluster or not. Okay, so today and probably also next week, we'll look at the EM algorithm. Gaussian mixtures. And I'm using these handouts, or not these handouts, I guess these notes from a different course, and instead of kind of the explanation in the book. So the EM algorithm is explained in our textbook, but I'm going to be using these notes, and I've posted them, or I linked them on CCLE, okay? EM algorithm for Gaussian mixtures, and this allows us the use of Gaussian distributions allows us to kind of account for kind of the shape of the distribution. Okay, and so, maybe an extreme example is, let's say we've got two-dimensional data that look something like this, and one cluster of points kind of making a cloud of points here. Something like this, and I guess I'll have another cloud of points clustered right there, and then another cloud of points, say, clustered right here, okay? And so if I said identify three clusters, it would be easy. We would just, like as a human, you would spot the three clusters very easily, right? If I said identify three clusters, as a human, it's very easy, okay? Okay, we would just say, there's a cluster up there, there's a cluster over there, and there's a cluster down there, okay? This would be cluster 1, 2, and 3, or something like that, right? If we had to do something like this. Okay, but if we did k-means clustering, with k-means clustering, we would run into some issues. What would happen? Well, with k-means clustering, it's going to kind of look at the distance, and it's going to say this point and this point, these two are more similar than this point and this point. Okay, so it looks at this and it looks at this, and maybe I don't want to draw directly on this thing. But k-means clustering kind of looks at the data here, and because it's using distance, it's going to say these 2 points are closer together. So they are similar. Okay? Whereas kind of this point and this point, these are kind of, those 2 points are far, so they don't belong together. Okay? Does that kind of make sense, what's going on? So because k-means clustering just uses Euclidean distance, it's going to end up grouping the, I don't know, these, it's going to group kind of these points over here along with these together, and these ones will go with these ones, and we'll probably get something separated like, I don't know, I'm going to guess something kind of like this. This will be one cluster, here will be another cluster, and you know, you'll have something kind of like that. Will be my guess for what happens with k-means clustering, right? And when we look at those results, that doesn't seem to make sense to us, right? Wikipedia's got a picture of this kind of phenomenon as well. EM algorithm. And they have cool animations here as well. Okay, and so here we've got kind of three blobs as well. And again, because k-means clustering uses just a distance, it ends up putting these points together in here, and these points up here, and with this cluster, whereas the EM algorithm allows us to take into account different shapes, and we will kind of cluster them according to the, you know, what seems to make sense. We're taking into account kind of the shape and the spread of the distribution. Right? So that's, huh?
What happened to the orange point?
What happened to the orange points? Let's see. Yeah, what are these orange points? Huh? These are, I think they're test cases. I think this is the original data, and these are kind of test cases, and they're seeing how the algorithm classifies these test cases. I think that's what these orange points are. And so k-means puts this one as red, and this one down here is red, whereas EM, well, I guess same results. They belong to the center cluster, but as far as this point, according to k-means, belongs to this cluster. This point right here belongs to here, but according to EM, this point would belong to the, I'm sorry, this point here would belong to the large cluster in the middle. And, you know, I guess we could debate how that works. Okay. All right, so the way it works is our data is it going to be a mixture, okay? So, so we model our data as a mixture of distributions. Okay, and so you can imagine, so kind of the data generating process says, you know, randomly choose let's say mixture distributions, and so we'll say randomly select a value, I don't know, 1, 2, or 3 if we've got 3 distributions, for a distribution of 3 for a mixture of 3 distributions. So let's say we've got a mixture of 3 distributions. We're going to just randomly select a value with probabilities, and then we'll say alpha, and we've got half come from distribution 1. I'll use decimals. So we'll say 0.5, 0.3, and say 0.2, or something like that, okay? So we're going to pick a distribution at random, okay? So we'll either pick distribution 1, 2, or 3, and then once you've selected a distribution, okay, generate a random value from the selected distribution. Okay, so it could be that distribution 1 maybe is multivariate normal with mean equal to 0, 0, and sigma matrix equal to, we'll say 9, 0, 0, and 9. Okay, and so what this looks like is basically just cloud, you know, cloud of points in a kind of in a circle, right? So that could be distribution 1. And then distribution 2, maybe this is, we'll have a multivariate normal, and maybe we've got mean equal to 4, 4, and our standard deviation here, maybe this is 1, 0.9, 0.9, and 1, or something like this, okay? And so, so this is centered at 0, 0. This one would be centered up here at 4, 4, and it would look kind of like this. So less spread, but there's high correlation or something like that. Okay, and then distribution 3. Maybe this is normal distribution. I'm just making stuff up here, okay? And we'll say the mean is equal to, I don't know, -4, -4, and the covariance matrix maybe is 2, -1, -1, and 2, or something like that, okay? Okay, so -4, -4 would kind of put us down here, and you'll have some covariance and like that. And so, you know, the combination of all of these will be, the result is going to be a mixture of these things, and and we can't actually see it ourselves. I mean, not so we can't see it ourselves. We're going to see it, but the points will be unlabeled. Okay, the points will just be all together. And so when you see a point, you won't know which of the three distributions it came from. It's just going to be one of these things. All right, and so I can just kind of generate some of this. All right, well, I'm going to use my, my incorrect operating set seed thing. Maybe we'll get this figured out, okay? And so I'm going to create kind of a vector for alpha, all right? And this is going to be 0.5, what did I say, 0.3 and 0.2, okay? And, all right, and then so for distribution 1, we have, so I'm going to call mean 1 will be 0, 0, and sigma 1 will be a matrix of, what did I say? 9, 0, 0, 9, 2 by 2. We'll just do 2, okay? That works. All right, so we've got mean 1, and then let's do mean 2, and mean 3. Okay, and then I forgot what I said. I said 4, 4, and then 1.9, 1.9, 0.9, and 1. And then mean 3 is -4, -4. And what did I say? 2 minus 1. I hope I don't run into any issues with these things. Okay, and then let's do library MVT norm. Okay, and so technically the data generating process should go something like let's say for I don't know, I in 1 through 1,000. I guess we'll produce X will be matrix of zeros with number of columns equal to 2 and n row equal to 1,000, and I should just do so technically we'll do K is going to be sample 1 through 3 with probability equal to alpha, okay? And then we'll say MVT norm. Oh, so RMV norm, and we need one value from using sigma or using mean and sigma, okay? And so what I'll do is I'll say I'm going to put all of these together in a list. Okay, so I've got means will be list of mean underscore 1, mean underscore 2, and mean underscore 3, and then sigmas will be a list of sigma 1, sigma 2, and sigma 3, okay? And then I guess I will just do means, and we'll pull out the kth means value, and sigma from sigmas we'll pull out the kth sigma value. I think this should work, right? And then we'll store this into X row I. This code makes sense to me, but we'll see if it runs. Oh, error. Okay. Recursive index failed at level 2. Let's see. So sigmas. What is sigmas? Sigmas looks good to me. And if I ask for 1, something break when I do k? K. Oh, that's why. Okay, so I just need from 1 through 3, I need one value of k. This is where the issue came in. Yeah, that's what I need. Okay, now it will work, I think. Okay, let's go ahead and we'll run this. Okay. Okay, so now it's done, and then let's go ahead and then let's plot x, and we'll say aspect ratio equal to 1. Ooh, this is a lot crazier than I thought it would look, okay? Okay, so we can kind of start to see a little bit, right? So the 9 was bigger than I thought, okay, as far as the variance goes, okay? So you've got kind of this big blob of points in the middle, okay, that represent kind of the thing centered at 0, 0. You can see very clearly there's the cluster here for the points that came from the centered at 4, 4 with covariance, high covariance, and then you can also see kind of a concentration here, right? And I didn't color this, but I suppose I could have like if I wanted to, I could paste together the add the value k in here. We'll just add a third column, okay? And then when I plot it, we can use, so we'll plot the first column by the second column, and then we'll say the color depends on k. I'm sorry, the third column, x comma 3. Okay, so let me go ahead and run this. I'm missing a comma. Thank you. Okay, and so you can see kind of all of this, but in the original plot, if I get rid of the coloring, okay, this remains a mystery to us. All right. And so this here is just a mixture, but we don't actually know that these ones come from over here, right? And so the question is, and if we did something like k-means clustering, it's just going to kind of group everything based on distance, okay? Can the EM algorithm actually pick out something down here? Maybe, I don't know. Will it pick this out and something like that, right? So this is kind of what we're dealing with. We've got a mixture of distributions. I might want to like tweak the values that I'm playing around with. Maybe I should have set this down to like 6. I'm just curious what this would look like. Okay. So it's okay. Well, I don't know. All right. So anyway, we can just, I guess, leave this for now. I'll save it later. Okay. So to express this as a kind of a mixture distribution, what we've got is, and I'm using the notation that appears in the EM algorithm notes here, is we're going to say the probability of kind of the vector x given all of our parameters here, and it uses kind of big theta here. This is going to be the sum of k equals 1 to k being the number of components that we have of alpha sub k times p sub k x given z sub k and theta k, all right? So, x is a two-dimensional vector. Okay. And k is the number of components. Which is, in our case, 3. All right. And then p sub k, all right, is kind of the probability density of kind of the k component. And z sub k is a kind of a vector of 0 and 1s to kind of indicate which component is at play, is being used. Okay, and so and we have to express it like this because let me copy this picture here. Let me just go to the next slide. Okay, is that when we look at some point like, what just happened? Okay, if we look at some point, let's highlight like this point right here. Okay, this point, the kind of the probability of this point okay is, you know, relatively high, right? Because it could, like this point could technically come from, could be from, you know, component 1, the central one, okay, and it has basically, you know, probability equal to, what is this, like whatever 3 comma probability of, you know, the point, let's say 3 comma 3 coming from normal distribution where 0, 0 is the mean and sigma is equal to 9009, okay? Or it could come from component 2, where you know, it's the probability of maybe you know, 3 comma 3 coming from a normal distribution where the center is 4, 4 and the standard deviation is 1, 0.9, 0.9, and 1, okay? And technically, it could also have come from the third thing, but like just be this really, really crazy outlier. But probably the probability of that is like so extremely small that we could ignore it, okay? But this point, we don't know if it came from this one or if it came from the big one, okay? It's a little bit hard to kind of classify. So we just have to kind of we're gonna just have to guess. And so the probability is going to be basically the sum of the component mixtures, okay? So the probability, the total probability of that point is going to equal basically the sum of alpha, the proportion of that component multiplied by the PDF of the component distribution. Okay. All right. And the theta sub k's that appear are just you know, the kind of these parameters, the mean and the standard deviations of these things, right? Does that make sense? And so the way we're going to run the algorithm, though, is that when we see a point like this, okay, when we discuss a point like this, we don't know which class that it belongs to or which component it belongs to, okay? And so if we knew, right? So if we had the answers where it's labeled like this, okay? And I said, all right, we've got a mixture of 3 components, you know, figure out the mean of this component and this sigma matrix. You know, that's easy. You just kind of take the mean of the points that belong to it, and you take the you know, MLE estimate of the sigma or whatever. You do the same thing for the ones that belong, okay? But we're in this situation where everything's unlabeled and we don't know which one it belongs to. And so when you have a point kind of like here where it could belong to one or it could belong to another, how do we say, should I include this value in the mean of this component, or should I include it in the value of the mean of this component, right? So if you've got something and you're like, well, it could belong to cluster 1, it could belong to cluster 2, the way we're going to find the mean of cluster 1 is basically taking the mean of all the points that belong to cluster 1. And the way we find the mean of cluster 2 is we take the mean of all the points that belong to cluster 2. So how are we supposed to do this if we don't know if a point belongs to cluster 1 or cluster 2? Okay, so what do you guys think we should do? Okay, so this is kind of the central problem that the EM algorithm solves, right? So can I put this back here? Okay, so here's our picture, all right? And we've got some point here. Okay, some point could belong to cluster 1, or it could belong to cluster 2. We don't know. Okay. You know, to find the mean of cluster 1, okay, at least we would take the mean of all the points that belong to cluster 1, okay, or the centroid, right? Take the mean of all points. Oh, and I'm already out of time. Okay, cluster 1, and then to find the mean of cluster 2, we would take the mean of all points in cluster 2. Okay, and so the question is, should this point be used in cluster 1? Cluster 1's mean calculation, or in cluster 2's mean calculation?
Whichever cluster has higher probability, in the sense of like which cluster has more points.
Okay, and so we have a suggestion. Constantine says we should do something about which cluster has higher probability. Okay, and well, we're going to do something like that, and basically we're going to use kind of like the Bayesian classifier to get a probabilistic assignment that this point belongs probabilistically 60% to cluster 1, 40% to cluster 2, and we'll weight its value in each cluster's mean calculation appropriately, okay? And I guess we'll do that next week. On Wednesday, have a great Memorial Day weekend. We'll see you guys on Wednesday, and we'll take a look at how this works.